Good morning. My name is Daniel Medeiros. I'm a postdoctoral researcher at the Computational Media Innovation Centre, Victoria University of Wellington, New Zealand. I'm here to present my recently TVCG published paper, Magic Carpet Interaction Fidelity for Flying in VR. This work has been done in the scope of my PhD thesis at the Instituto Superior Técnico University of Lisbon. So as VR gear has become more widely available, effective travel techniques have also risen in importance. Travel or locomotion is the act of translating people from one point to the other in the virtual scene in a given direction. Travel is one of the most common and universal interaction tasks in 3D interfaces and often supports another task than being an end on itself. These include actions such as selecting, manipulating, and interaction with objects in the 3D scene. To evaluate travel, Bowman et al. Proposed quality factors which include ease of learning, spatial awareness, appropriate use of speed, accuracy, and presence. One of the main classifications for travel techniques is by task decomposition, which separate travel phases by the act of indicating direction, controlling speed of movement, and input conditions, which indicates how the movement is initiated, continued, and terminated. A way to approach travel in VR is by addressing with a fidelity, which is a concept which relates to how close real-world sensory stimuli are reproduced. When dealing with the way people interact, this concept is called interaction fidelity. So the higher level of interaction fidelity a travel technique has, the closer it is to the way people walk in real life. Work by Mac et al. Shows that the use of a high interaction fidelity technique, such as the human joystick, which emulates the joystick but using people's bodies, can improve efficiency when using VR technology. However, objects may result out of reach, and in remote locations after VE, and natural metaphors alone are not sufficient to support travel. In these cases, users may need to use flying metaphors to reach these spots. One problem with this type of approach is the unnatural control of multiple degrees of freedom to support locomotion. Some attempts of flying is by using machines such as a paraglider, a spaceship, a zero-gravity simulator of Burley, where the user fly by flapping their virtual wings. However, the use of such equipment limits users to the action of traveling, which may not be suited for complex VEs, where users need to perform further actions such as object selection and manipulation. One example is the work by Wong et al., who uses a balance board to control flight in VEs. However, the use of leaning to control direction of flight led to 25% of the users to quit the test due to severe cybersecurity side effects. Another example is the work by Bowman, where the users explore techniques that users indicate direction use their heads or hands and found similar results for both techniques. However, results are still preliminary as the virtual environment users did not include any obstacles and users were not able to see their own bodies. We argue that the decoupling between direction indication and speed control enable to isolate the unnatural part of travel, which is the control of 6 degrees of freedom, enable the use of high interaction fidelity techniques for speed control, which can improve the effectiveness of the flying experience. When using high interaction fidelity techniques in VR, users need to be fully represented by an avatar in the virtual environment, as the user need instant feedback. The use of an avatar also makes it easiest to people locate themselves inside of VE and affect their space judgments. So in this paper, we evaluate how interaction influence quality factors such as efficacy, spatial awareness on flying travel tasks. For that, we developed the Magic Carpet design space, which combines a fully embodied representation with a floor proxy to avoid imbalance issues. This design space enables the use of interaction fidelity of metaphors for flying. To assess the best performing techniques on both interaction indication and speed control, we conducted 2 different studies, one for each phase. The best performing technique on the direction indication phase was then used as means to indicate direction on the speed control study. So in this study, we used an Oculus Rift TK2 as an input device and 5 Kinects to provide body tracking, which are merged into one coordinate system using the Creepy Tracker toolkit. We limited the carpet size as a subset of the available tracking space to provide a reliable tracking space. We use an abstract mesh avatar as the first person, and this avatar was used for both male and female participants. This avatar was selected as an abstract avatar as an output of the study presented on the paper Keep My Head on My Shoulders from ASM VRST 2018, which indicates the graphical fidelity of the avatar in the first person does not really affect travel quality factors. So in the first study, we recruited 18 participants, and two of which were female. The ages of the users varied from 21 to 35, and 13 had previous experience with VR. We implemented 3 different techniques for direction indication, and on all of the techniques, the speed was limited to 3 meters per second. So we chose this speed to isolate the direction indication phase and not induce cyber sickness effects, and a 1 was used to trigger movement. The first technique tested was a novel technique called elevator plus steering, which uses a degrees of freedom separation strategy to control direction, which is a common approach in mid-air manipulation techniques to improve precision, such as using the work by Mendes et al. On this technique, the direction on the horizontal plane is controlled by the projection of user's gaze on the horizontal plane. Additional buttons were used to control direction on the vertical plane. On the gaze, we could control the direction using the direction of the heads, and on the hand technique by the orientation of the user's hands. So due to Kinect's limitations, we attached a reflective rigid body to be able to track our 3D wand using a 12 OptiTrack Flex 3 camera rig, and this was mapped into the user's dominant hand. To guide users through the scene, we positioned rings to indicate the desired path. Only 1 ring was shown at a time, and once crossed successfully or not, that ring disappeared and a new ring appeared in the predefined location. This test consists of 22 rings along a path with a length of 180 meters and include average changes in the Z coordinate. To compare the techniques, we used the metrics time, collision time, number of collisions, path length, and 6 Likert scale questionnaire responses for subjective metrics. For the continuous variables, we used the Shapiro-Wilk test to set data normality, and because the samples were not normally distributed, we used the Friedman non-parametric test to identify mean effects. Then we used Wilcox-Consign ranks with Bonferroni correction. We also used Wilcox-Consign ranks on the questionnaires. So in this test, we found that the elevator plus steering technique had the worst results in our tests. It was the least efficient technique in terms of total time, because the users spent most of their time colliding with objects. It was also the technique with the longest travel distance among the 3 tested techniques. The results for the gaze and hand-oriented steering were similar to those found by Bowman, where the gaze technique had the advantage in terms of distance traveled, and the hand advantage in collision time. Additionally, users indicated that the hand technique allowed them to be more aware of the presence of a virtual body, which corroborates with a short amount of collision time. The participants also found it easier to indicate direction of movement and to navigate in the virtual environment using the hand technique as indicated by the questionnaires. Another advantage of the hand technique is that it enables the decoupling between movement and camera control, enable him or her to inspect the virtual scene while traveling. So we can indicate that the hand technique was the best performing technique to indicate direction. So in the second study, we assessed the impact of the use of high interaction fidelity techniques for controlling speed when flying. The test design and methodology used in this test were similar to those in the previous study. We also recruited 18 participants, 2 of which are female. The ages varied from 21 to 35, and the majority of them had previous experience. We also used the same virtual environments and presented the tasks similar to that in the previous experiment, but following a different path. This path was longer, measuring 330 meters, and contained abrupt changes in the Z position. We also incorporated more complex maneuvers, such as U-turns, to force users to carefully control their speeds while they flew. As a result of the previous study, we used the hand as means to indicate direction. The upper limit speed was 5 meters per second, and this study, we tested 3 different techniques for speed control. The joystick, where the speed was controlled through the analog joystick, the speed circle, and we also used 2 different techniques with a high level interaction fidelity. The speed circle, which similar to the human joystick, as inspired by McMahon et al. And in this technique, users closest to the border of the circle have maximum speed. So we rendered an additional circles in yellow to prevent users from stepping outside the circle when reaching the maximum speed zone. The circle is divided in positive and negative halves, which are updated according to the user's orientation. and only when users were on the positive side of the circle, they were able to control speed of movement. This feature makes the movement stop when making abrupt movements, such as U-turns. People could prevent this by moving their body while they're traveling or by walking forward in the circle when the movement stopped. To avoid this, we explained this limitation before users perform the training tasks and asked them to perform these maneuvers during the training task. And the last technique was the walking in place, which emulates the action of walking but remaining stationary. So to compare these techniques, we also use the metrics time, collision time, number of collisions, path lengths, speed variation, and 6 Likert scale questionnaire response for subjective metrics. We also used a similar statistical analysis from the last user study. And as a result, in our test, we noticed that users experience more difficulty in coordinating the direction indication and speed control phases with the walking in place technique. Consequently, they had more difficulty to control speed, as more participants stopped the speed control movement when they reached the ring, then pointed to the next ring and then flew to it. With this technique, users also felt more cyber sickness. And regarding embodiment, users felt less control of their virtual bodies with the walking in place. This may be attributed to the noise in the depth sensor signals. Another interesting point reported by the participants was that they lost balancing in some cases because of the weight compensation that occurred naturally during their gait in real life, for which the emulated experience did not entirely match the actual experience. With this, we can infer that walking in place was the least suitable technique in terms of task performance in comparison to the other, but still efficient. The joystick technique was found to be generally the most effective, efficient, and this may be explained by the familiarity the users already had with video games. However, in most cases, the users did not finally control the speed, as indicated in the figure, but instead maintained the maximum speed most of the time. We can also report that joystick rotations did not induce increased cyber sickness in flying tasks, as opposed to room scale VR. And the speed circle was not the most efficient technique, but in this technique, they had a more precise control of speed, including abrupt movements. People also pointed that more training could improve their performance with the speed circle technique, as people reported that they got lost in the circle, but quickly compensated by recentering themselves. They also stated that they need to periodically look down at the circle, which affected their performance. Previous work indicates that high interaction fidelity techniques can translate into quality factors in ground constraint scenarios when VR technology is used. But we found that interaction fidelity does not always translate into quality factors in this type of tasks. Although the joystick has been proved optimal for using such as applications based on our tests, we can still identify the speed circle technique as a good alternative when more precise speed control is required. So in this paper, we can conclude that we proposed and validated our magic carpet design space, and we can say that the design space is indeed an effective way to fly in VR and enable the use of high interaction fidelity techniques for flying by decoupling the natural control of multiple degrees of freedom. Inside a design space, we can notice that high interaction fidelity techniques can improve quality factors, especially when a more precise speed control is required. But this kind of technique not always translates into quality factors. So this leaves us with the opportunity to explore the magic carpet by using state-of-the-art techniques for travel, or even proposing novel techniques for flying inside a design space. So as I conclude, I finally wanted to thank everybody that was involved in this work, the participants and also my colleagues, and also everybody that is seeing this talk around the world. Thank you. So if you have more questions, please email me after this talk. Thank you.